cloud. Okay, so for the brine recirculation MSF system, we said that the heat recovery section is very much similar to what we've seen in the once-through system. We just call this MR instead of MF, and it will be heated to a temperature that we may call it as TR1. Then this is going to be heated further to T node, which is the top brine temperature. Actually, this should have been T node, not TR. Top brine temperature of the unit. After that, flashing is going to start, and it will decrease in a value of delta T for every stage. We assume this delta T is constant, and similarly, upon the assumptions of neglecting the boiling point elevation effect and assuming that the vapor temperature is equal to the effect temperature, we could come up with the equality of delta T in this section, upper part, and delta T right here. So again, that was basically the same as we did for the once-through system. That could enable us to do many simplifications of the model, leading to come up with the sensible to latent ratio, which is basically HFG of the vapor, which is evaluated at some average temperature in the middle of the plant. Accordingly, we could get, based on this value of Y, or the sensible to latent heat ratio, we could come up with expressions of the membrane, expressions of MR as a function of M dot distillate. And that was great because we could find an expression that can tell me what is the value of the distillate production at stage I, and what is the value of the brine leaving any stage I, and what is the temperature at any stage I, be it temperature of the flashing brine or temperature of the preheated or heated flow of the recirculated water as it passes here. So that's something we could find last time, sort of expressions that can directly give us these relations immediately. So we don't have to do the analysis of, say, it's 19 plus 3, 22, or 21 plus 3, 24 stages. You don't have to solve the system of equations for everything to get it, but this is a simplified solution. Yes, we admit that it has simplifications, but it gives some sort of a quick estimation to what is really going on within the plant. If you need to do more accurate work, then you are going to come, this is basically the sample of the stage, and that basically the kind of analysis that we have gone through last time. And this is the analysis of the brine heater to the right, which basically would be the same exactly as we did for the once-through system. Now, when it comes to the analysis, definitely delta T again is assumed based on constant temperature drop across every stage, and this is typically and practically acceptable. Now, when it comes to this one, if you don't want to do the simplifications, if you don't want to assume TVI is equal to TI in this equation, which is an approximation, and we know that it is not 100% accurate, because the difference between these is basically lying in the boiling point elevation, and we neglected the boiling point elevation in this equation. If you want to consider it, you would not be able to simplify the equation, and then you have to come up with, you cannot come up with a closed form solution. It will be too complicated. So what you need to do is solve the detailed model in equations and in unknowns, and then you'll be able to generate a table that will get the values here. But doing that, we could be able to take CPTI common, assuming that they are the same, and then we'll have sigma DI plus BI, which is nothing but the value of M dot R. And the same thing here. So that we have M dot R CP here and here and here. When we cancel them together, then basically you are ending up with this delta TI is equal to delta TRI. This is a good approximation, and it's a simplifying one. Then we could, based on that, get the value of TR at any location. What is this? This is basically the temperature of the water which is being flowing inside these tube bundles from stage to stage. Then we can get it at any time. Of course, this is TR1, which is right here, but we can get TR at any one of these locations here, leaving any stage and entering to any stage. So that's something that we could generalize and get an expression for based on the assumptions that we have done in the heat balance equation that led to the fact that delta T and delta TR are the same. And then for the heat rejection section, we did the same, but for the heat rejection section, look at the heat recovery section. We could find here, this is basically MR, this is MR. In the heat rejection section, these parameters are going to be the same, but whatever is passing inside the tubes in the heat rejection section is not going to be MR, but instead, it is going to be MF plus M cooling water. So we can do the same. We can also assume TVI and TI is the same, which means that we assume that the boiling point elevation effect is approaching zero. Accordingly, temperatures are the same. And we can combine this to M dot R and this to M dot R, but here one we cannot because this is M dot feed and M dot cooling water, which means that the temperature difference here in the flashing part at the bottom of the stage is not going to equal to the temperature difference on the top side where the flow is passing inside the tubes. But there will be a ratio, and this ratio is basically would be given in terms of MR over M dot feed plus M dot cooling water. And this is the one I meant here. So for the heat rejection section, this is new. We did not have a heat rejection section in the once-through system, but for this one, we have it. And the relation between delta T, if I'm talking about the heat rejection section, which is made up of 3 stages, the delta T here and the delta T are across these stages are not going to be equal, but they are related by this equation as we see it here. And definitely the value of delta TR is going to be different. For example, if this temperature is 25 and this temperature is 40, then we have a delta T per stage here as 5 degrees centigrade, whereas the delta T here still can be something like 2.5 or 3, depending on the number of stages and the top and bottom temperatures. And this is basically, actually there are 3 stages, so you can easily get the value of the temperature at any location. It will be, for example, here it will be the seawater temperature, here seawater plus delta T, here seawater plus 2 delta T, and this is it. So you don't really need a recurrence relation for it, but it's just for the sake of making things complete. The analysis here for the stage are going to be the same as we did for the once-through system, was just, as I mentioned, we are going to replace the M dot feed by M dot R. So DI, the distillate at any stage, can be given as a function of the sensible to latent heat ratio, the recirculated mass flow rate of the brine, 1 minus y to the power I minus 1, where I here is the stage number. You are staying at stage number I, number 10. So I is 10, so this is 9, and then you can get the value of D9 or D10, sorry, at one stage. The total amount of distillate, how it is related to the MR, is given here, which is a generalization. It's a natural evolvement of this equation to that. And this helps a lot in our problems, because we are going to see an example that we are going to solve it numerically, and we'll see that we are going to make use of this equation. If we know the value of M dot distillate, then we try to come up with the value of delta T, and then knowing the value of CP, knowing the value of HFG, and calculating delta T. These are all what is needed to make the value of Y. Once you know the value of Y and you know M dot distillate, then you can get M dot R immediately. And that's another benefit. The mass balance in the heat rejection section, we have seen it last time, and we've done it with an example that talks about the numbers as they are getting in and out, be it brine coming from the heat recovery section, or feed which is recirculating to enter to the last stage, blow down, as well as the quantity of distillate which is leaving. We don't have to talk about I mean, again, talking about the brine, because basically this is what you do. Talking about the heat recovery section, that is stage number 1, for example, and this is stage number 2. In stage number 1, there is a vapor moving up, which is D1. In stage number 2, we have vapor, which is this. If I need, for example, how much is the brine leaving this to this, leaving stage number 2 to stage number 3, it would be basically what is coming here is MR at top brine temperature. So here I can say that B2 should be M dot R minus D1 and D2, because this is the quantity that entered here. It has lost D1 for evaporation, it has lost D2 for the evaporation, and the remainder is going here. And the equation can be generalized in this form. Salinity expression is just following the equation. All you have to do is just take each one of these components and multiply it by its salinity. So BIXI is this quantity into XR. Last time also we did the analysis for around the whole plant, and we have looked at what is in and what's out, taken a whole control volume. In that control volume, there is the brine heater, the heat recovery section, and the heat rejection section. And we're looking at what crosses the system boundary. M dot steam crosses the system boundary in and out. We have M dot distillate crossing the system boundary. M dot rejected brine crosses the system boundary. Seawater, which is being heated and will be thrown away, is going to cross the system boundary. M dot feed does not, so it will not. And accordingly, we have looked at the energy balance for each component here, and we came up with this expression. As you can see it here, definitely I did not mention that the combination of this presentation is very sensitive to the touch of the pen. So basically this is M dot feed plus M dot cooling water is entering here. The M dot cooling water is thrown away. M dot blown down is thrown away. M dot distillate is obtained as a product. And here we have M dot steam entering and leaving the unit. So making the balance for each one of these components is going to lead to this equation, which is a very good opportunity that will enable us to calculate the value of M dot of the cooling water. Brine heater, nothing's new here. We're talking about a heat exchanger. In heat exchanger, we are having steam coming in and steam leaving. M dot steam coming in as saturated vapor, leaving a saturated liquid. While it is doing that, it is heating M dot R from TR1 to T0. So the temperature profile is going to be this, T steam, and it heats the fluid from TR1 to the top brine temperature T0. You can write the expression of the log mean temperature difference based on that. This is delta T1, this is delta T2, and you can calculate the LMTD. And Q is basically M dot S into HFG of the steam, and Q also is M dot R into CP delta T, sensible heating of the seawater as it comes in. And Q also is, in addition to that, it is the overall heat transfer coefficient for the brine heater, area for the brine heater into log mean temperature difference for the brine heater. And if you wish, UB can be obtained using this expression here. Or you can have it as a value, or you can get it as, in the former way, a combination of conduction and convection resistances. For every stage, we consider the surface area for every stage is the same. So what we do, we take one stage from the heat recovery section, let it be the first stage, and we do similar analysis to it. So this is, say if this is stage number 1. So basically D1 is going up, it will condense here, so the Q1 is D1 into HFG1. HFG1 is evaluated at temperature TV1. So here we have TV1 is going to heat the fluid from TR2 to TR1. Then you can calculate the log mean temperature difference. The difference between TR1 and TR2 is basically the delta T, which is known, and we know how to calculate TR1, so we can simply get these values here. TV1 is T1 minus boiling point elevation. Knowing the value of T1, we can get the value of TV1 right away. Then we can get the area here because Q1, which is given by this, is equal to the overall heat transfer coefficient in stage number 1 into the area of stage number 1 into U1. So that is going to make Q1. Q1 also is M dot R Cp into delta T. So we can also get Q this way. So this is just an expression of what I just mentioned here of how to obtain the area here. The area of the heat recovery section is going to be the area of stage number 1 multiplied by the number of stages in the heat recovery section. If at the end I'm looking for the specific heat transfer area, I would say that this is area of the brine heater plus A1 into N minus J. N is the total number of stages, J is the number of stages in the heat rejection section, plus A of the heat rejection section, NA1 in the heat rejection section multiplied by J, number of stages in the heat rejection section. This is going to be the total surface area needed in the plant divided by M dot distillate. So that will get us the specific heat transfer area. For the calculations of the area in the heat rejection section, interestingly, we can just look at the heat rejection section. 3 stages, yes, we know. Let's take 1 stages of these. Take the last one as an example. The inlet is M dot cooling water or seawater. This one at T cooling water and M dot cooling water plus M dot F. This is the kind of flow rate which is coming in. The temperature here is T cooling water. This is T cooling water plus delta Tj, which is the temperature difference between this and this. This is Tn divided by the 3, the number of stages. Then the temperature here is Tn, and the vapor is coming at a temperature Tvn, and the vapor quantity is nothing but Dn, which is, if it's 24 stages, it will be D24. Then the same analysis that we have done earlier will be applied here. We are going to come up with a log mean temperature difference. We have a value of the overall heat transfer coefficient, and we're going to calculate the area accordingly. So it's just a repetition, but the only difference here is that the value of delta T is different, and accordingly, we don't expect the areas to be exactly the same as the heat recovery section. But the procedure remains the same. Stage dimensions, nothing new. Whatever you have done in the once-through system is going to be applied here. Calculating the gate height, the brine pool height, and the width and length of the stage. So this is typically what we do for the analysis here. So it's just slightly different compared to the once-through system, but it is, the heat recovery section is pretty much the same. The heat rejection section is the one that has some changes due to the difference in the flow rates. At the bottom, we have the brine, which is being decreased from one stage to the other, but at the top, inside the tubes, it is not M dot R, but it is M dot feed plus M dot cooling water. Interestingly, this is the first ever MSF plant that was built. It was built in 1957 in Kuwait. The one who made the analysis for it or the design was Silver. Silver was one of the, I would say, the pioneers in thermal desalination systems. He's the one who patented the idea of MSF building, as you can see it here, and the patents were registered both in US and UK. And they made a tender for the MSF for 2 units. Each one is 1 million gallons per day in Kuwait. And they have 3 decks, cross-tube arrangement, brine recirculation, 19 stages. The PR of the plant was 6, and it was commissioned and put into operation in 1960. So that was the first. It started in 1957, but it started operation at 1960. So the picture is not very clear, but this is the clearest one. We're glad that we could have this picture anyway, just to as some sort of a documentation to the first plant that has been operated with this technology. That is, typical layout of the plant as well, keeping into consideration that this is the brine heater, and we have pumps that are moving the condensate away, and pumps that are taking the brine recirculated back again to the unit, and pumps that takes care of the blow down to throw it away, and pumps to take the product into the I would say either tanks or distribution system. What is not given here is the pumps that are bringing the seawater in. So that is a sort of interesting way of making like a block diagram of the unit as well. And here there is some major differences in the tubes layout, which is the longitudinal tubes, which is the one that we see here to the right, versus the cross tubes. The current technology is having the cross tubes, so that the flow passes like this back and forth from one stage to the other. This is basically the feed or the brine recycled flow. This kind of arrangement that we have, which is typically what we see here, has very good benefits, which is if there's a problem of the tube bundle, the problem is going to be only in a certain stage. So you know you are going to fix it only, or fix the problem in this stage. Maybe replace the tube bundle here in that stage and keep it working. So in terms of maintenance, it's fine. The problem associated with this layout is that the pressure losses are huge, because we have so many minor losses. We have bends. This kind of blue thing normally extends outside the stage, and it is normally not insulated. So maybe done with a material like stainless steel that has a thermal conductivity of 15, which is not very high. But anyway, it might be losing some energy to the surroundings, in addition to the pressure loss due to the bends that we have here. But in terms of analysis, in terms of maintenance, it's easy to maintain. On the other hand, look at the long tube distiller, which is this one. The tubes are extended over several stages. If some tubes are blocked or broken, then it will not only affecting, you don't have to do maintenance in only one stage, but you have to do it for extended number of stages. This is one of the drawbacks, but the pressure loss is much less here. It's only some sort of major losses due to the friction, but you don't have minor losses due to the bends and moving back and forth. And now I can see the modern designs and looking for enhancements of the performance of the unit by reducing the amount of energy needed to run the pumps is going into the direction of using long tube distillers. So that actually is much less in the pressure drop, and smaller pumps would be required to operate it. This is typical numbers that the seawater TDS, total dissolved salts, is in the order between 35 to 47. Actually, here they are 46 in the Gulf, by the way, so we are in the upper limit, and sometimes it slightly exceeds that. As of today, the maximum brine temperature is 112 in the running units, in the commercially producing units. Why I'm saying that? Because some units are not commercially producing, and they are only like pilot units for testing. This is where you can test different types of rust inhibitors and anti-foaming and anti-scaling kind of agents or chemical compounds, and then you can try 120, and there are pilot units that are operating 120, and some have been tried with 130 as well, using nanotechnology as a pre-treatment case. But the problem with nanotechnology is that because you have to drive the seawater across the membranes, the nanomembranes, that you need additional power, which is tremendous. I mean, if we are going to apply something like in the order of 30 bars, then let it be all RO. You just increase it to 60, 70 bars, and then you can have the system. But having heat and substantial amount of pumps, and then additional pumping for the nanotechnology, that makes the energy price so much for these units. Performance ratio is somewhere between 8 and 11, although there have been sort of ideas, but I've seen it in papers talking about optimization of this system that can bring the PR to higher values than that. But typically, it's somewhere between 9 to 9.5 for the modern or for the new units that are there. Electric power is 3 to 4 kilowatt hour per cubic meter. People working with RO claim that all you need is something like 2.3 or 2.2 kilowatt hour to desalinate the water. Looking at that and making a simple comparison will say that without heating, less than the electrical power needed for the MSF, you have much less power than that, and it can run an RO system for desalination. And that actually what has been driving the SWCC here in the kingdom to move also into the idea of the RO. They have just been into the Guinness record this month, or actually that was in March, by recording, I think it was 2.2 kilowatt hour per cubic meter in one of the RO units that we have here in the kingdom that has been commissioned lately, which means that this can be done, but you have to guarantee good quality of intake water to have low power for the RO. If you are going to run into the problems of the water, the intake water, this value might increase and reach up to 8 kilowatt hour per cubic meter, as some of the engineers have been mentioning in some places that they have RO units and the kilowatt hour per cubic meter is quite high. I have to tell you that the MED unit is just needing something close to the 4 kilowatt hour per cubic meter to operate with all pumps and heating requirements. So the MSF basically is more demanding in terms of power, but it is the most reliable and the most experienced kind of desalination technology. The quality of the water is pure, better than the RO definitely, because it's basically evaporation and condensation. So you're talking about pure water. If you need water for a feed water heater in a power plant, you cannot take it from an RO system, but you might take it from a system like this. And you are going to use this kind of unit as long as you have a power plant which is using steam. Then water is not going to cost you a lot because the steam is there, and the steam is our source of energy. You've just seen the latest, the very first one that has been built in between 57 and 60. Now this is the latest that has been placed in Ras Al Khair. You can see it here. It's the whole unit is coming here. You can see here it's a cross tube flow for the feed, and it came like this. It was not connected together in plant. This is the one in Ras Al Khair. You can see the trucks that are there, the yellow things at the bottom or the orange color here. These are the trucks that were made specially to carry this about 3 to 4, it weighs 4,150 tons. And all of this came on the ship as is, and it has been moved and placed in location and operated as one unit, which was quite an adventure, having to do something like that and bring the unit as a whole-made unit and putting it here, rather than putting it piece to piece. It is 123 meters long, it is 33.7 meters wide, and the weight is more than 4,000 tons. This is huge. I mean, you are as if you are just moving a very large building from one place to the other. That is amazing, being able to take it and bring it in Ras Al Khair and put it to service as one unit. Some plants, talking about the analysis and evaluation of performance of some of the MSF plants in the Middle East, the plant availability is very high. What does it mean, availability? It means look at the number of hours over the year where the plant is up and running. This is more than 90%. RO technology cannot do that, cannot have this kind of high plant factor. That's something which is associated with MED. The lifetime, as I told you before, it was supposed to be like 25 years, but actually now they are approaching 40 years of operation and the performance is still the same. So there is a kind of tremendous experience that has been built around this technology and people know well how to keep it running. So a positive kind of experience, even reaching 40 years of operation for this kind of technology. This is some information about Jabal Ali station in Emirates. It's a plant at the west coast of Dubai in Emirates. It was constructed in 1994 with 8 MSF units. And then 5 years later, 1 unit was added to improve the performance and optimize energy analysis so that it can have an overall production of 67.5 million gallons per day. And the details of phase 1 versus phase 2 are being shown here. Phase 1 is 8 units. Each unit is made up of several number of stages, definitely. And phase 2 is just 1 unit that has been added. The year of operation between 94 and 2000. The unit production is made the same. So the same production for every unit is kept. Overall production is 272,700 cubic meters per day. This is for the 8 units. If you divide this by 8, it should tell you how much each unit is producing, and that's something which is, I can do it here quickly. So we're talking about 272,700 divided by 8. So each unit is producing 34,000. So the one that has been added is exactly having the same kind of production as well. The performance ratio was not recorded for the old ones, but for the new one, it's 8.5. No data are given for the specific power consumption for running the pumps. And it's been operated by adding it to a power plant. Here we have a gas turbine, and in this one, there's a steam turbine running it. It's a gas turbine heat recovery steam generation as well. And then the vessel material was carbon steel covered with stainless steel, which is the same as you can see it in this one. And the tube material was basically copper, nickel, and aluminum brass kind of material that are being used for running this unit. So that was an idea about the model and something about the oldest and the newest kind of technologies for the MSF. I have a couple of things still that are left with us here for our class today, but maybe before them I can make just a couple of announcements. One of them, I put the results of the midterm exam on the blackboard already. So the exam was graded out of 100, but I reported the grades out of 85. So there was something like a 15 marks given as bonus in the exam. So that's something I'm just thinking of a way to make the papers available to you. Maybe I can scan it and email it to every one of you, and that's I'll try to work on that. This is one thing. Next week on, I think our next class will be done with Ramadan has started already. So كل عام وأنتم بخير. And you know that in Ramadan, we are going to start the class at 9 p.m. Definitely it's after iftar, but I'm not sure whether it will be after Taraweeh or maybe in the middle of Taraweeh. But anyway, this is our class starting time. That will be from the beginning of Ramadan, inshallah. Still, our class on Monday will be the same at 5:20. And one more thing that we need to think of is that we need to think of our next quiz. Maybe we can think of a quiz toward next Wednesday. And the material for the quiz would be the multi-stage flash desalination system. Today we're done with the multi-stage flash desalination system. Maybe a few things will be left after the example. Maybe I can have time to share something with you, or maybe I can keep it for next time. It depends on the time left. And I've already called for one of the scientists in the SWCC. His basically name is Dr. M. Dr. M used to work for quite a bit of time in Doosan. Doosan is a Korean company. It's a multinational, I mean multi business kind of company, which is doing very huge work in construction and in building desalination plants. So they used to build MSF and MED plants in the past. Dr. M is working now for the Research Institute of SWCC. I just dropped him a message so that he can give a talk to us and talk about what is the latest activities that they are doing or interested in SWCC, which is basically something related to what is known as brine mining. So let's see if he can talk to us a little bit about brine mining, and that's something that we're going to discover, which means that we take the brine and without rejecting the brine to the sea, what we do is that we're trying to convert it into salt crystals that would be having an economical value. And this actually is some sort of a fashion which is being spread recently, and the whole world is interested in that. So I just hope that Dr. M can talk to us about this. The last time I called Dr. M to give a talk to my class, it was several years ago. He was still in Doosan, and he was talking about their latest technology of MSF and MED. Now it's not anymore. He's a part of SWCC, and you'll enjoy his talk. I'm just trying to confirm where he will join us, and then I will let you know. So initially, we'll have a quiz next Wednesday. If Dr. M decided to join us on Wednesday, maybe we can shift the quiz for the next class. So we'll see that. It will be clear in our at the beginning of next week, inshallah. Next Wednesday, I would expect an additional assignment, which is giving me an update to what you have done with your project. So if I'll make like a way to submit it through the Blackboard. If you have got some results, I'd like to look at the results. If you have started to develop the model, let me see what you have done with the model, and so on. So that is basically what I would expect on Wednesday. I'll open like an assignment in Blackboard, and the due date will be this Wednesday, inshallah. Any questions so far? If not, then I would move into an example that would cover the topic of the MSF system. So that we're talking about an MSF brine recirculation system that has 19 heat recovery stages and 3 heat rejection stages. So 19 plus 3, the total number is 22 stages. It has the following information. X feed is 34,000 ppm. X brine is 68,000 ppm. Cooling water temperature is 25 centigrade. Yeah, TS, steam temperature, is taken as 100 centigrade. Tn is 35 degrees centigrade, which is the temperature at the last stage. Productivity is expected to be 1 kilogram per second. Thermal temperature difference, cold, is 3 degrees centigrade. Delta T loss is 1.5 degrees centigrade. HFG of steam is 2256 kilojoule per kilogram Kelvin or centigrade. HFG vapor is, let me extend this for a while. HFG vapor is 2354 kilojoule per kilogram. Yeah, overall heat transfer coefficient for the brine heater is 2 kilowatt per meter square centigrade. And for the condensing tubes, it is 1.9 kilowatt per meter square centigrade. Boiling point elevation is 0.9. So this is the kind of data that are given for the plant, and there's something here that we don't have to get it, but we would know that the average temperature is somewhere the average between the top brine temperature and the bottom brine temperature, or the rejected brine temperature, which is the average temperature at which HFG, for example, has been calculated. What is needed to be calculated in this example is basically steam flow rate, m dot steam, is needed. M dot feed is needed. What else? Let me look at this. M dot rejected brine is needed. MR recirculated brine is needed. Actually, the recirculated brine was the first thing needed here in this problem. Anyway, does not make much difference the order that it has been requested. Brine, heat transfer area, condenser area in the heat recovery section, condenser area of the heat rejection section, the distilled flashed at stage number 10, and the brine rejected at stage number 8. So that's typically kind of requirements that would be associated with MSF system. So here, oh, sorry. Maybe I can put it here as calculate those values. Then, to get to the solution of this, there are things that typically you would do always. For example, we should start by calculating delta T stage. And delta T stage would be nothing but T naught minus Tn divided by the number of stages. In our case, T naught is it given? Let me check, because if it's not given, that should have been provided in the problem. That maybe I can put it separately here. T naught is 90 degrees centigrade. So this is going to be 90 minus 35 divided by n. What's the value of n? We have 19 plus 3. We have 22 stages. So the delta T as 2.5 degrees centigrade has been calculated here. And we need this value. We need the delta T. Why? Because we need y. Who remembers what y is?
Cp delta T over HFG.
Yes, I mean, what I'm expecting is that it is basically the ratio of the sensible to the latent heat. So Cp into delta T stage divided by HFG average. So doing that, you can calculate the value to be 0.004. And the value of y is important. The kind of equation where you are going to use y is like this equation, the relation, for example, MD relation to the MR that's going to be given to you. So MD is equal to MR. This is an equation that you should not memorize. 1 minus y all to the power n. Doing that, what we know? We know the value of m dot distillate, it's 1. We know the value of y, which is 0.004. We know the value of n, which is 22. So from here, we can calculate the value of mr, and it calculates as 11.74 kilogram per second. Now, when we think of the steam flow rate, what would we do? What is the component that we think of whenever it comes to talking about steam flow rate?
Brine heater.
Exactly, we do an energy balance of brine heater so that M steam into HFG steam, this is the energy given, and this energy given is required to heat MR from TR1 to T naught. So T naught minus TR1. So here in this equation, we have two unknowns. We don't know the M dot steam, and we don't know the value of TR1. But we can get the TR1 value quickly. I should have, yeah, I cannot, once I've done the equation, I think I cannot do changes into it. Can I? Oh, yes, I can. I just want to make them far away from each other so that it doesn't look like a one word, BHMS. So MS into HFG is equal to MR CP T naught minus TR1. TR1, if you remember, if we are considering something like the heat recovery section, the heat recovery section here we have basically what is coming in is MR, M dot R, and it is coming in with a temperature Tn, and then it should be heated here to TR1. The number of stages that we have here is 19 because this is the heat rejection section. So I can say here that TR1 is equal to Tn plus 19 into delta T, because the temperature increases in each one of these by a value of delta T. So delta T into this number is 19. We have 19 here, and we have 3 in the heat rejection section. So from here we can get the value of TR1. And the TR1, once you get it, it will calculate to 82.5 degrees Celsius. From here, we have HFG, we know it. We know the value of MR. We know CP. I think it was given somewhere. If it's not, you can assume it. Is it there? Maybe not. So you can calculate the value of CP, and you can take a CP as, actually, I'm not sure whether I take it, because normally we take it either 4.2 or 3.8 in our calculations. I'm not having it with me. Let's say that, but it might be the other one. Then doing that, knowing the value of T naught as 90, TR1 is 82.5. So from here we can calculate the value of M dot steam and the m dot steam accordingly can calculate to 0.1482 kilogram per second. Knowing the value of m dot steam, it will enable us to calculate the performance ratio, which is m dot distillate over m dot steam. M dot distillate is 1, m dot steam is 0.1482, so the value here is going to be 6.7 as a performance ratio. Then, having done that, we are going to go back again to the old equation that we used earlier, which is basically talking about m dot feed is equal to md plus mb, and m feed into x feed is equal to mb into xb. What do we know out of these? We know the values of m dot, we have a mistake here. This actually should have been plus. We know the value of m dot d, and we know xf and xb. So the only two unknowns that we have here are basically going to be m dot feed and m dot b. So doing that, we can calculate it to get the value of m dot feed is 2 and m dot b is 1 kilogram per second. So now we could get m dot r, m dot steam, m dot feed, and m dot b. The next thing to do is look at the areas. Here we have areas and flow rates that are needed. Maybe flow rates are easy to calculate. We can start with them. I mean, all are easy, but they are just shorter. So if I take these out, and for the flow rates, I'm going to use equations that have been developed. Again, the relation between the distillate production and the MR, and there is a relations that we have used to do that, so that we would know, for example, that D10 is equal to MR, mass flow rate of the recycled brine, into Y into 1 minus Y to the power I minus 1, which is 9. Look at this. We know the value of MR we obtained in the first step. We know the value of Y, 0.004. So from here, we can get the value of D10 right away. And the value is 0.046, approximately, kilogram per second. And this is one of the nice things about the analysis that we have done. Now, in just one step, you can know what each stage is approximately producing, and approximately is due to the assumptions that you have done with the system. Then, talking about brine leaving stage number 8, this is going to be basically m dot r minus the quantity that has evaporated here. So I need to calculate the vapor that has evaporated from stage number 1 to stage number 8. So that this vapor, or D from 1 to 8, can be calculated again by similar expressions to what we have done or what we have developed during the model development. Or this is 1 minus y to the power I here, which is 8. And this is 0.374 kilogram per second. So B8 is m dot r that we calculated earlier minus this quantity, and accordingly, it is going to become 11.36 kilogram per second. So far, what has been a trick that has been not used in this example is something related to the utilization of the overall balance. For example, this example did not ask for how much is m dot of the cooling water. If this has been asked, then you could have looked at the whole power plant or the whole desalination plant as your control volume. This is what I started with talking about today, that this is the brine heater, this is the heat recovery section, this is the heat rejection section. Look at what's in and what's out of this unit, and then you can come up with a balanced equation that has the m dot cooling water as a part of it. And this is where you can calculate the m dot cooling water. I did not ask for it for this example, but you might see that in one problem or one example or so. I don't have to go through the details of area calculations. Maybe we can look at one of them. Let's take one of the stages in the heat recovery section. The brine heater, you have seen it before in several occasions. We have done the brine heater for the single effect evaporation or single stage flash system, as well as the one through system. So let's consider this unit, which is the heat recovery section, and look at the first effect in this section. We know the value of TR1. The value of entering here is nothing but TR2. And normally, TR2 is equal to TR1 minus delta T. The temperature here is T1. T1 is T naught minus delta T. And TV1 is T1 minus boiling point elevation. So this is basically TV1, which is going to heat the fluid from TR2 to TR1. The fluid here which is heated is nothing but m dot r. This is what's passing inside the tubes. Accordingly, delta T1 is TV1 minus TR2. Delta T2 is TV1 minus TR1. The log mean temperature difference is nothing but d delta T1 minus delta T2 over ln delta T1 over delta T2. You can calculate the value of the log mean temperature difference here, and the value would be something like 5.25 degrees Celsius. Q1. You can obtain Q1 by one of two ways. Either you can say it's m dot r into Cp into delta T, which is m dot r is moving here. It will be heated from TR2 to TR1. So the difference between them is delta T. And then you can get the value of Q1. Or you could have said that this is equal to D1 HFG 1. If you need to get it accurately, HFG, will have HFG average, which you can use it as an approximate value. So these are, you can calculate the value from either one of these if you have the value of D1. And also this is equal to U1 into the area 1 into the log mean temperature difference 1. U1, you can take the value of UC, which is given in the problem. LMTD, we have calculated it here, so that the only unknown becomes A1. Then area of the heat recovery section is equal to A1 times 19. We have 19 stages recovery section. Then after that, you are going to go to the heat rejection section. The delta T there is different. It's entering as 25, leaving at 35, which is Tn. So it will be 10 divided by 3. Just to make it a little bit clearer, I would just say here that I don't have to do it in details for the heat rejection section, but I'm just pointing it out. It is made up of 3 stages. The temperature here, Tn is 35, which means that TVn is 35 minus boiling point elevation. And the temperature entering here is entering at 25 degrees centigrade. And it will be heated from 25 to this temperature. What is this temperature? It will be the 25 plus delta T J, delta T of the heat rejection section. This is 35, which means that the temperature here is 35. So delta T for the heat rejection section is that difference, 35 minus 25 divided by the number of stages is 3. So 10 minus 3 is 3.3 degrees centigrade. So the temperature here is expected to be 28.3 degrees centigrade. This is the temperature here. This is here. This is the vapor temperature, 35 minus boiling point elevation. Then you can come up with the log mean temperature difference here. Overall heat transfer coefficient, you are going to take the same value of UC given to you, and then you can come up with the calculations of the area. To calculate Q, you can calculate it from the flow passing here, but in order to do that, you should know what is the value of m dot cooling water, which we did not calculate, and it was not needed, but maybe you can get it from D24. How to get D24? It's from the relations that D I is basically equal to MR Y into 1 minus Y to the power I minus 1. Does this apply here? Think with me. Does this equation apply here? What do you think, ya shabab? Does it apply in the heat ejection section? I'm getting no answers. What do you think? The equation has been developed with m dot r passing inside the tubes. The tubes
It's not applicable yet.
m dot r.
It's not applicable.
So I don't think it applies here. So you cannot make use of this equation, which means that you can either develop a similar equation for the D24 for the heat rejection section by writing the balance equation for the heat rejection section and getting the relations between them, or simply you can make a balance over the whole plant and get the value of m dot cooling water. And then you can substitute here, get the value Q24, and then back again to this expression, which is overall heat transfer coefficient into the area of stage 24 into the log mean temperature difference of 24. I think that would make more sense to do it this way. So we are going to make an energy balance around the whole plant as one control volume, calculate the value of m dot cooling water, and then calculate how much Q that has been heated by the vapor that's condensing on the outside surface of the tubes. That would make more sense to do. Okay. Any questions? Is it clear or not?
Yes, no.
Yes,
Means
doctor.
that basically we have now the tools in our hands that we can use for analyzing problems that are associated with the brine recirculation MSF system. For the ones through MSF system, it's exactly the same, but we do not have a brine recirculation part. We don't have a heat rejection part, which means that it is more simpler to go through the once through system compared to this. We don't have time to show you the other presentation that I was preparing. Maybe I can start with this. It will take something like 20 to 30 minutes of our next class. And the interesting thing about it is it actually expresses some of the work that one of your colleagues have done in his master thesis. He was basically working with SWCC and doing like a part-time master in our department. His name is Musa Asiri, and Musa's work actually was interesting in the sense that he did something which is related to the field that he's working in. He's working in SWCC, and his thesis was basically related to MSF systems. So we're talking about the performance improvement possibility by using a thermovapor compression. When you look into the literature, you'll find that there are people that have proposed the use of thermal vapor compressors or TVC with MSF, but we have done that differently. And that difference has resulted in a substantial improvement in the MSF performance. The only problem that we had is that by the time he finished his work, we were talking to the SWCC people, why don't you make use of this and try it in one of the old plants that you have? And we're certain that this is going to improve the performance. But by that time, they were just thinking in one direction, which is the RO. They don't want to hear about, they don't want to put any investment in the MSF technology, although it might be, it may pay back. But again, that's something that, I mean, we cannot force that. That's something which is